And next up, we have Alexey talking about Turbo-Geth. And he'll just be covering sort of all the latest improvements and performance updates that have been added to the Turbo-Geth project. And he is in this room, so I'll let him introduce himself and kick off with the presentation. Welcome, Alexey.
Hello, hi Karthik. Thank you very much for the introduction. And yeah, so I will, let me just start the screen share. I will sort of say a couple of words about, one second, let me just figure it out. Yeah. Okay, so first, a little bit about myself. I basically, I'm currently, I've been a programmer for pretty much all my professional life, and for almost last 3 years, I was working on this particular software, just called Turbo-Geth. And what Turbo-Geth is basically, it started as a fork, of the go-ethereum, and sort of experimental software with certain goals to basically make it a bit more performant, if possible. And but now it's becoming more different, and we're going to see in our talk how and why. And the title basically is Too Good to Be True, is addressing the something that I haven't thought about until very recently, is that whenever we present some kind of performance numbers for Turbo-Geth, most of the time the first question I get, where's the trade-off? Like, what's the catch? What is the, because people think, well, if we do something better, then we have to do something worse. And so basically that's what I want to address. So here's the picture about the, so in the databases, I look at the, first of all, I look at Ethereum as a database, essentially. It's a distributed database with certain properties. But in the databases, essentially, you have usually like 3 points between which you're making trade-offs. So update efficiency, space efficiency, and access efficiency. And sometimes, of course, the space efficiency helps all others. And yeah, you can kind of move around and trade one for another. Usually, you might have seen those triangles as well in different areas. And so, people normally think about moving in this little plane, which is the circle underneath. And so this is where you're going to get trade-off, like, oh, if I get more efficient in access, I must be losing something in some other places. But what actually happens in technology all the time, and if you look at it, there's always technologies which are strictly improving, right? We have seen this many times. For example, move from SSD to HDD. First of all, the SSD were more expensive, but now they're SSDs for considerable volumes, they're not so expensive anymore, and they're pretty much better at everything. So nobody's asking what is the trade-off between SSD and HDD, at least not anymore. So this happens all the time in technology, and usually the way I see it is that the previous technology is a bit further apart, away from this efficient frontier where you can do trade-offs. And so usually you want to get closer to the efficient frontier, and that normally requires some kind of paradigm shift. And the paradigm shift is usually also kind of goes against the common intuition. So we're gonna look at this. So what kind of the paradigms did we have to shift here to, which I posit that we did get closer to the efficient frontier. So there are a little bit of trade-offs, but not many. So next time, that's why every time people ask me the questions, what is a trade-off? This is what I'm bringing up. So we're going to be talking about the paradigm shift in the data model, where we replace trees with the flat data. We're not going to be talking about history, the data model for history, because it's another complex topic, and then I'm not going to cover it today. But we are going to be talking about other things like concurrency and architecture. So with the concurrency is essentially whether you do homogeneous concurrency, essentially when you're trying to run many things at once, but they're pretty similar? Or do you want to run like lots of different things at once? That's what I call the heterogeneous concurrency. And in terms of architecture, it's here you basically the shift is from a monolithic system with a lot of cross-cutting concerns done in the name of optimization. We're moving towards the modular system with the separate concerns, which I posit as well is more optimal. So we start with the data model. And so kind of I thought about this for a very long time. Like, where does this come from? Where does these data model come from that everybody's using? And some time ago, I saw that it actually probably comes from the yellow paper. And again, it comes from a sort of common intuition that yellow paper essentially calls this particular way of storing data that most implementations do right now a sensible implementation or a reasonable implementation. And it says that it's memoizing the function C, which is essentially function C is mapping the nodes in that sort of state trie into their sort of hashes or something like that. But actually it should probably be the inverse. So although these paragraphs are not normative, they already create this sort of, they basically based on somebody's intuition or some sort of common kind of expectation. And therefore everybody assumes, I guess everybody assumes this is how we should implement this. And this is where it goes. So back in 2017, when I just started this project, I started with profiling go-ethereum, and I bumped into this thing, which was 20% of my profile. And this is exactly accessing this memoized function, memoized inverse of a function C. So essentially, given a hash, you need to figure out what is the node, the tree node is. So basically, that's the, so in the previous slide, we were talking about recommendation to memoize this function, and here we're actually using this memoization. And that was from my point of view, that was a performance bottleneck, and this is where all that started. So, and this is the picture you probably saw many times, some of you. So on the left is basically my very simplistic representation of the state trie, where you have some elements which are V1, V2, V3, so forth, and they are built up into this kind of sophisticated, I would say, state trie. And the arrows, the black arrows in that the tree on the left are the those function, like memoizations of this inverse function. So given the root hash, I can get this root element and so forth, and I can navigate through. So for example, if we wanted to find element V5, so we need to basically access this memoization 1, 2, 3, 4 times. So that's basically 4 access to the database if you use this memoization as a data model. And what I noticed straight away is that I couldn't parallelize this because there is a data dependency there. So you don't know, you cannot do the, don't do the second arrow until you resolve the first one. So there is necessarily data dependency and no possible parallelization. And on the right, you can see how this memoization kind of is laid out in a database if it's a key value store. So yeah, and so here's another point, is that you're essentially the deeper the tree, the worse the problem is becoming. But why? Why does this? Why do we actually have to do this at all? And it turns out this is all about computing the state root hash, which we need to either, if you're a miner, you have to place it in header, or if you are just a verifier of the block, you have to compare what you've computed with what you got in the header. So all of this complexity is simply to verify the state root hash. And this is actually one of the interesting innovation of Ethereum compared to Bitcoin, which essentially commits every block we commit to the state root. And this is actually quite a good, interesting feature, but it has a certain cost. And apparently, so I posit that the cost of implementing it in the old way is actually very high, and it's unnecessary high. So what does the So now, what does the EVM think about it? So if we look at it from the EVM point of view, so if you looked at the, like, what is the EVM opcodes are, they actually have no idea about the trie. So they don't actually look at the trie. They look at the account addresses, and they want to fetch balances, bytecodes, or storage and stuff like this, and also some instructions for storage loading. They look at the addresses, they look at storage location. There's no merkleization here at all. So so basically what the hypothesis was that, okay, having everything stored, having the state stored in a radix tree as a primary structure, it tries to satisfy this sort of computation of the state root, which I think is quite a minimal thing. And but it sacrifices the efficiency of EVM access. As we saw before, it requires the sequential data-dependent access. So is this sacrifice worth it? So essentially, we sacrifice EVM efficiency and to be able to compute these state root hashes quickly. And that's what Yellow Paper calls sensible or reasonable implementation. So yeah, that's what I've been working on for last 2 years, is that trying to figure out if this is a sensible or reasonable, or could it be that this is a false trade-off? And now I am convinced that this is a false trade-off, because it is possible to do both things efficiently, to compute the state root and have efficient EVM access. Okay, so but how do we do that? So we know how, if we have a flat data structure, I don't need to explain you how to provide the efficient state access from EVM, because it's clear. Like if you go back to the slide, if this is exactly how we store the data, EVM simply accesses it in this form. So I don't need to tell you how this works, but I do want to tell you how the other part works. So given the flat structure, how do we calculate the state root? So yeah, if we know the structure of the tree, then we can do that. And of course, you can try to build up the tree and then compute the root, but obviously that is going to be quite memory intensive. What you could do better is that you can start some kind of stack, and then you need to calculate the tree, let's say from the left, and then you only keep the stack of 1, 2, 3, 4, 5 hashes. And then every time you move on, you just append, like you are accumulating sort of the hashes on a certain level. So you can basically compute this whole thing with a very limited memory. So with about five accumulators for hashes and so forth. But that's still quite large. I mean, I can tell you that, for example, it says in SSD, it might take you, I don't know, half an hour or something like this, or sometimes an hour to get, depending on the speed, to essentially iterate through entire state and compute the state root. So although it's sort of relatively quick, but it's not as quick as you can't do it for every single block, right? It's too slow. And so the problem then becomes is that, okay, what if we had the root calculated, and we had maybe we cached the part of that state tree in memory, but because we don't store it in database, once we flush the memory, it's gone. And then we needed to in our block, we needed to modify this green thing, and then sort of like, how do we actually calculate the new state root? How do we do that? So originally, this is how I was doing it. I would essentially load the entire region of the flat structure, the entire one, and then I would calculate the root. And that was, well, that kind of worked as long as as my kind of cache of the state was large enough. And in the beginning, it was terribly slow, like on a startup. And but then it was also, if the block started to hit some cold spaces in the state, it was quite slow. But I sort of thought, okay, I'm going to solve this problem later. So I was running with it. I was saying, okay, I know that it's really crap right in the moment, but I know we're going to solve this because I had this idea how to solve it. So this next slide shows how we're going to discard this data, because we just used it to compute the state root of that little subtree, and then we discard it. Okay, so the solution that I was thinking about all that time, but I just didn't have time to implement it. But now it's all implemented, by the way. So now it's all done and dusted. So we going to store what I call the intermediate hashes. So it's sort of, you might think that, oh, but this is actually going back the direction of these trees. Actually, no, because in the tree that the yellow paper suggests to do, we are mapping the hashes into the nodes. But here the mapping is kind of opposite, not opposite, but slightly in reverse. So we're mapping the prefixes in the trees to the hashes. So essentially, the function that this particular structure serves is simply to have those hashes, and we store them in the database. Yeah, and the storage is also, I would say that it has a nice properties because it's got the data locality and things like this, and that's also pretty small. So now, if we need to solve exactly the same problem, if we have this green thing that we modified and we don't have, the pieces of the trees around it in our cache, so we can use this structure, new structure that we introduced, to help us to bridge the gaps. And so that's how we do it. We load only those things that I pointed out with the arrows from the database instead of the entire region. And here we go, and we can basically compute our new state root. So this has been implemented this year quite recently, I think about April or something, or May, and it has been optimized multiple times. So now I show you what is the cost of that, right? And also I'm going to show you how our storage looks like. So the structure, the additional structure that I was talking about just now, it's called intermediate hashes. It's currently for the reasonably recent state is about two something gigabytes. So actually, it's not a bad price to pay for this, right? And it is the structure which essentially stores all the intermediate hashes for all the levels of this tree and stuff like that. And so you can also notice that there are two structures for the state. That's another innovation which we introduced quite recently. So we store the state twice, but why? So first we store the state as a plain structure, which is currently 9.09 gigabytes, maybe a bit more right now. And then we have a hash state. So some of you may know that in order to keep the kind of the tree balanced, we need to apply some hashes to the keys before we put in the structure. So we separate these two things. So EVM actually works with the plain state, and then in order to produce the state root again, only then we use the hash state. So we convert it to the hash state, and then we compute the hash there. But we have managed to get rid of there was another table here which is called pre-images. So because we have the two states, we actually don't need the pre-images. And there are some other nice properties about it. For example, it allows us to withstand certain DOS attacks easier than other implementations. So yeah, so as I said, I'm not going to touch on the history storage, but it's also pretty efficient. And so all in all, the efficiency in storage actually translates into efficiency of access as well, because things are simply smaller, and then they're actually more kind of standard, so you can look them up quicker. So now we go into the second paradigm, which is the concurrency. And so here is something which kind of was discovered again this year, is that on the top you basically could see how the things were processed before in go-ethereum and in Turbo-Geth before that time. And you can see that when we download the blocks, there are, let's say, some sort of stages of processing. For example, we do recover we recover senders from the signature, so forth, and we do certain things like run EVM through it and compute some storage root or whatever it is. And so usually this happens sort of in parallel with this kind of staggered concurrency, and lots of things are happening in parallel. And so what we did is that we decided to split them up in like this. And of course, intuition would tell you that this is actually slower. If you just look at this diagram, it's like, oh no, this is definitely going to be slower. Actually, it probably was a bit slower in the beginning, but then because we managed to split them into more homogeneous pieces, we were able to actually make the individual pieces are faster, and in the end, everything was much faster, maybe like 10 times. Again, this is another paradigm shift, which you go into the counterintuitive direction, and then you arrive at the kind of a next level result. And so this is the stage sync. So what basically happens here is that we are trying to process, especially when we do the initial sync, we try to process things in large batches, as large as possible. So for example, if I would sync right now, my first batch would be more than 11 million blocks. So I first put this 11 million blocks through the first stage, and then another million in the whole batch through the second stage, and so forth. And so because we do that, and so in the red I just put here some text, is that because we're putting most of these stages are actually essentially data transformation. They take the data from one table and database, they do something with it and put it in another table of data in the database. That's why I'm calling Ethereum a database. So, but with the databases that we use, is that it's actually easier. It's actually much more faster to put that stuff in the database if it's pre-sorted. So, in other words, databases are pretty. You should not use them for sorting. So there are much better sorting algorithms. And so what that basically graph means that we can use that property to speed up the sync quite a lot. And so, but if you, let's say, process one block at a time, then the time is not going to be so impressive. But it would be very impressive if you start processing million a block at a time. And this also explains why our implementation actually can work with HDD sync, which hard drives. Actually, one is currently just on a finishing line right now. I started almost 30 years ago. Sorry, not years, 30 days ago. Sorry, and it's today is finally catching up with the tip of the chain. But when it catches up, it's not going to be able to process every single block through the stages. What it will do, which I tested before, is that it will, so you see this intersection here, it's for example, for my HDD, it will be about 15 blocks. It means that it cannot process, one single block quicker than 13 seconds, but it can process 15 blocks approximately at the same speed as these 15 blocks are produced on the mainnet. And so this is where we find the intersection. So my HDD sync would be always having a lag of about 15 blocks, but for some application it's probably all right. I mean, but as I say that because SSDs are so much easier now, so much faster, and then because we don't require you to have 5 terabytes, so you can actually buy a pretty cheap SSD and run it, so you don't need HDD. So it's pretty much for academic purposes at the moment. And I think by the time our size grows to 2 terabytes, you're probably going to be able to afford SSD at the same price as it's now for 1 terabyte or something like that. So anyway, so that then we go to the third paradigm shift is the architecture. So I put a note here about core dev calls in July 2020. Some of you might have listened to those calls. So for 3 calls in a row, we decided to not discuss the IPs for Berlin, but talk about other issues, about kind of wider issues. And we talked about the developer burnout, we talked about development process and things like this, about the client diversity. And so maybe some people think it was completely useless, but actually I thought it was really, really good. And I learned, I found it very informative, and I made some conclusions out of it. And so one thing we debated on the call is that whether the modularization and splitting things in component would actually help. And so there were opinions on the call with saying that if you start splitting things up, you will lose the optimizations, because there was assumption that optimizations have to be cross-cutting, and they basically like tie everything together, and then eventually it becomes a big spaghetti. But my experience is actually the opposite. And there was one person on the call actually agreed with me. And so this is where we are on a journey to make this happen. And so as you can see here is that 1 thing is already done, 2 things in progress, 1 thing will be started. And actually on the right here is that the stage sync is also part of that. So it's also kind of componentization. So, and one of the interesting things about this architecture is that it hopefully will allow us to bring more developers into the project and into the core development in general. It does actually also lead to certain sort of abdication of power from the core developers. But that's it's a bit larger topic, and I would probably discuss it in somewhere else in a kind of more long form, or whatever, chats and podcasts and stuff like that. Then the last slide, which is a bit of a, you probably heard about or seen me talking about 10x improvement in Ethereum. So, and today I just realized that, oh, you know, why is it, can't we go from Ethereum 1x to Ethereum 10x, or some x, maybe 2x. So, and so if we actually take it seriously, then there are, from my point of view, three main challenges here. So it's a nice goal to have, of course, to do 10x on layer 1. But there are three main challenges which I sort of describe here. I'm probably not going to unpack all of them for you, but they're DOS attacks, and there are certain DOS attacks we know about, and some of them are because of the state access, but some of them are computational. Some of them are related to precompiles, and that's thanks to Vitalik to pointing out to me. So we're currently actually assessing those things. I mean, I know that some groups are doing the same thing, but we're assessing it in the context of Turbo-Geth. We are finding more attacks, and we're trying to figure out how to protect against them. And so we just recently started this effort. And then there are other things that, there are other two things that people are worried about, but I think they are also solvable. So on this point, I think I'm going to end my presentation, and I don't know if you have any time left. Sorry, guys. I think I might have.
Thank you so much, Alexey. We do have a few minutes for questions, and we actually have a lot of questions coming in. So what we'll do is I'll just kind of ask a few here, and if we end up running out of time, I'll just ask you to join the live chat on live.ethonline.org, and you can just answer them directly there.
All right.
So handful of clarifications, a handful of broader, bigger questions. The first one being, does double hashing attempt to address any long-term state degradation related issues?
I'm not sure about the double hashing, but I don't know. I'm not sure what it means, what is meant by double hashing, to be honest. Sorry.
I think this comment will reach the audience in about 30 seconds, so I'll just have them see and clarify this. But in the meantime, I'll just move on to the next question, and that is, so it's, I mean, you kind of talked about that it's taken about 3 years to kind of get where you are. Purely out of curiosity, what was like the most surprising breakthrough in that time from kind of your perspective?
I think the stage sync was the most surprising thing, because I kind of thought, I discovered very early on that data model would be beneficial. It's just that with the data model, essentially the reason why it took so long is because it's sort of like in engineering, you solve one problem, but then you get another 2 problems to solve, and then you solve those 2, and then there's another 3. And so I wasn't sure whether this sort of, I will be able to tie all the loose ends in the end. And then I only figured out like last year that we will be able to tie all the loose ends and it will work. But generally, I thought it would be it would work. But with the stage sync, for example, or now with the components, that was quite surprising to me, that such simple things actually make such a huge impact.
That's awesome. I guess maybe a follow-up on that. How many people are currently kind of helping you with being a contributor to Turbo-Geth?
Right. So it's actually, the team has grown quite quickly, and so specifically this year. So we currently have about 13 people who are basically working on it, like 10 full-time, 3 part-time. And most of the time I'm losing count, because I'm actually inviting people all the time. And the reason I'm inviting people more all the time, because I do want to test this idea that if we do things in components, we can have many more contributors, which are sort of, they're not just waiting for the pull request to be merged, but they are there to develop their components, maybe on multiple different implementations of the same component, and so forth. So I'm actually up for testing the theory that we could have a much wider contribution.
No, it's awesome. It's a wonderful problem to have when you're scoring too fast and you get a track who's fully contributing. So that's wonderful. Another question that sort of came from the answer you just gave, and that is, what was the actual original intuition that sort of made you even try stage sync in the first place? Was it just experimentation?
Oh,
Or
it was essentially, yeah, that's a good question, because what I was, so basically I was profiling Turbo-Geth all the time. At some point I got to the place where the writes to the disk were the bottleneck at some point. And obviously, as I normally do that, I started to split, like luckily the database we had allowed us to look at the, like a write churn, like I call the write churn, how much data you write for each table rather than on the entire database. And I noticed certain tables were very intensive in terms of writing. And so those were, I saw that those were the ones that they had a very sort of randomized keys. So for example, the transaction lookup one, where if you have a transaction hash, you can figure out which block this transaction in. And obviously the keys being a transaction hashes are pretty randomized. And so we were inserting those randomized hashes within the middle of the table. And I was scratching my head thinking, maybe if we tried to pre-sort them, like if we just take the whole bunch of them, like 900 million of them, pre-sort them by hash and insert them that way, is it going to be faster? And it turned out to be faster. And this whole thing generated essentially the stage sync. It required a bit of a bravery, because in order to push it through, we had to delay the release, and we had to rip everything apart and then change the architecture entirely in about 2 months. It was actually kind of risky thing to do, because some people said, no, you shouldn't do that. You should just like release and then change it. But no, if I release, I'm never going to change this. I have to do it right now. And I think it sort of paid off.
absolutely. No, high risk, high reward, and I'm glad that you did. Last question for today before we move on to our next talk, and that is, I mean, it's a pretty big core value in our space that people should be able to run and kind of individually run and validate nodes, and kind of especially from like the Genesis block. So what are your kind of thoughts on this as a norm? And is one of the motivations behind Turbo-Geth to actually make this world a lot more possible, or is it purely?
I mean, it wasn't started for this reason. I mean, I simply wanted to create a better technology. I don't really like. I don't know if it's going to be the norm, because maybe if we do, like, let's say it's 10x, maybe we will make it impossible again to essentially we improve the technology, but we use it for not to let everybody run a node on their Raspberry Pi, but maybe we're gonna use it to expand the boundaries of the system instead, right? So I don't know. It's not for me to kind of make this sort of into ideology. I think I just want to make a better technology, and we'll see how this is what it's going to do. Is it going to make people run Raspberry Pis, or is it going to make Ethereum 10 times bigger, right? So.
No, that's wonderful. I think you're taking the stance of being a technology maximalist, and that's awesome. So there's a few more questions that are in our chat, so I'd encourage you to just kind of reply in the chat directly. And I want to thank you again for doing this talk and answering all of our questions, and a lot of excitement on the chat. So thank you so much, Alexey.
Thank you. Bye-bye.